want to start this conversation about big data by sort of setting the context for what analysts do with big data. We're here to talk about R, which is more involved with the analysis of data than the sort of engineering requirements that go with data. So from our experience with in-house and also talking to clients and customers, we get the picture that the life cycle of an analysis project goes through similar stages no matter what the project is. You normally begin with some sort of disruption or problem that you need to solve. And the first step to go about solving that is become familiar with the data that's at your disposal, try to refine the question that you're actually attempting to solve, and come up with a template solution. After you have an idea of what it is you want to do, then you can work on developing that solution, usually by creating some sort of model. The development step here often requires iteration, fine-tuning, getting things precisely the way you want them. After you've done that, if you are not the person who's going to be using that model all the time, you might need to productize what you've built, either automating it so a third person can use it, or integrating it into an existing workflow or business pipeline. And then finally, you'll need to disseminate the results by publishing them, either handing them off to a manager or whatnot. And even if you're just doing something simple like looking at some data and generating information for a decision maker to use, you're still going to productize and publish your results because you're going to create tables and graphs for the decision maker to look at. They're not going to probably implement the model, and you're going to have to give those to them somehow. Now, if you think of these stages, you realize R does have a lot to offer. For each of these stages, you could use base R and R's packages to explore your data and to fit a model and fine-tune a model. And then there's other things R can do to help you productize and publish your results. Some examples that I'm familiar with since I work for R Studios, you could use the Shiny package to make a literal data product, an automated analysis tool that anyone can use to explore data and implement your model. And then you can use packages such as R Markdown, Knit, or Sweave, and so on to publish your work in a very easy way. And the reason R works for all these things is because R is a language that's very useful for manipulating data, but also a full scripting language in its own right. And I think that's important to realize when you start to talk about big data with R, because R is a language, but it's not necessarily a piece of software that's designed to store data. And it's certainly not a piece of software that's designed for the specific problem of storing big data. A typical use case in R would be along the lines of temporarily loading your data into R so you could work with your data and manipulate it. And while your data is there, R is going to hold your data in your computer's RAM, the working memory. So this gives our users a very clear, bright line definition of what big data is. We don't have to think about the 5 V's, velocity, volume, value, all that. We can just ask ourselves, is our data larger than our computer's RAM? It's a very precise definition, but it's also somewhat ambiguous because think about your computer's RAM. How much RAM is on your computer? How much RAM could be on your computer if you added more RAM to it? And if you moved your work over to a server, well, then how much RAM could you have? It is possible to have quite a bit of RAM these days. But let's assume that you're working with truly massive data that exceeds your computer's ability to hold it in the working memory. How does this change what you do with an analysis project? What we've also seen from experience, and again from talking to customers and clients, is that there's 2 big changes that big data might put into this analysis workflow. And the first of those is, before you begin to work with your data, you almost always subset the data so you have a smaller data set that you can explore, work with, develop your model on. You could consider this training data, working data, what have you. If you're not subsetting your data, there's a good chance you're not really working with a big data problem, because big data by nature is hard to work with in its entirety and uneconomical to work with in its entirety. So usually you subset the data to make rapid progress in the beginning. Then maybe after you come up with a working model that you're satisfied with, you'd scale up that model to utilize the entire data set. And what this scale up step looks like will depend on your workflow and what you're doing. It's not necessarily converting to Hadoop or whatnot, but just some sort of effort to apply the model that works on your subset to the entire data set. And I say that you might only do this sometimes because when you look at what analysts actually do with big data, you see it doesn't always involve scaling up data. In fact, we found it particularly helpful to classify the problems that analysts have when it comes to big data into 3 categories. And this taxonomy seems to be pretty useful and versatile. So these aren't problems that IT has with big data. IT needs to worry about storing data, accessing data, putting it somewhere. These are problems that analysts have with big data. And if you think about what you do with big data, Probably the largest class of problems involves just extracting a data set from your big data. So you can imagine maybe you want to build a model of recommendations for a customer, and you have information about thousands and thousands of customers, millions of customers, but really the only information you need at that moment is information about people similar to the customer you're trying to build a recommendation for. So you have to find a way to find that information and get it. And then once you have your subset of data, your big data problem might resolve into just a regular data problem. The second class of data problems starts when you have an algorithm that you need to apply to the entire big data set. But in these problems, you can apply the algorithm in parallel to different parts of the data set. Sometimes these are called embarrassingly parallel problems. And then the final class of big data problems that we see analysts facing is when you have an algorithm or a model of some variety that you need to apply to the entire data set, but you can't parallelize it. These problems are called irretrievably big, and they're certainly one of the most difficult problems to work with big data, to use all of the data at once. If we think about how those problems fit into the life cycle of an analysis project, the subsetting step at the start of a big data project is a class 1 problem, just extracting a subset of data. And since almost every big data problem begins by taking a subset, these class 1 problems end up being much more common than class 2 or class 3 problems. From an R standpoint, that's great news because the class 1 problems are easier to solve in most cases than class 2 problems, class 3 problems. And again, class 2 is easier to solve than class 3 problems. There are many data problems that don't proceed beyond this step. Once you get the subset, you could go forward. But some problems do require you to take the model that you have and scale it up to use all of your data. And those are the class 2 and class 3 problems. Now, my background is in statistics, and I know people don't always agree with this or like to hear this, but I have a lot of faith in sampling. I know that you could do as much with sample data. Well, I don't want to say as much as with the large data set, but the efficiency and the performance you get from data samples can approach the performance you get from using the entire data set in a quite admirable way. And I think that really you only face class 2 and class 3 problems if you have a model that you do need to ramp up to use with other data, the rest of the data set. Anyways, this is the context we're working with. And what we're going to look at today for the rest of the time is how to solve these green steps with R. Each of these steps involves data that cannot fit in your computer's RAM, which means it cannot really fit into your R session by itself. You're going to have to store it somewhere else, and R is going to have to work with that storage software. If you've used R for a while, you'll know that this isn't uncommon. R has been used as a glue language for quite a while. And by that I mean that R, as a scripting language, has a lot of nice APIs to other languages and other pieces of software. It's easy to drive an experience from inside of R that connects to C++ or Hadoop or Fortran or whatnot. This is something that's been part of R's nature for a while, so the idea that we're going to work with R to talk to data that's stored in a different piece of software is not far-fetched, and it's not beyond the pale of what our users do anyways. Our general strategy for big data, this is the strategy that I recommend you use as an R user, is of course, store your big data in a data warehouse. If it's a truly massive data set, store it in some sort of data store that's designed to handle very, very large data. And there are a number of different options out there for you. Once you do that, R will have to communicate to our data store. So here I have R over here on the left, and this is just my generalized version of a server farm somewhere in the cloud. That's our big data store. Our two options for working with data in the data store is one, we could take subsets of data from our data warehouse that are small enough to pass into R, and then just work with them inside of R as if they're small data sets, which they will be. And then our second option is we could take R code and pass it into the data warehouse for the data warehouse to apply to our data where it lives. There are some data warehouses out there that are designed to use R code, but more often than not, you'll have to transform your R code into a language that the data warehouse already uses. If you go out there and take a look, there are many big data warehouse solutions that are already designed to work with R. And you should expect this list to grow. Businesses have come to recognize that open source software is very useful in general, and that R is specifically useful for analyzing data. And it's become a selling feature now to design your database or your data store such that analysts can use R to analyze the data in your database. That's something businesses are pursuing, and I'm seeing it more and more when I go out to conferences and that sort of thing. But even if you're using a data store that isn't purposely designed to work with R, you can still use R with the database. And that's what we're going to look at today. So when you have this set up, you spend most of your time working in R at the R command line, and you communicate to your data warehouse through a package. Use an R package as an API to the data warehouse. There are many different packages out there that provide APIs to many different types of data warehouses. For example, some of the most popular ones include dplyr, DBI, R Hadoop, Spark R. And this is just the tip of the iceberg. So I'm not recommending any specific package here, but I'm going to use the dplyr package in today's demo because the general principles involved will be the same no matter what you use. What we're going to do is we're going to store data in Amazon Redshift, a database in the cloud. You'll notice that wasn't one of the databases I listed as databases set up to use R, but we're still going to use it anyways. We're going to use the dplyr package as an API. I have a data set of data from airlines. We're not really going to look too closely at the data, but it's worth knowing it's about 20 years of data of every airplane flight in the United States that happened between 1987 and 2008. And it talks about whether the flight was delayed, where it was going, what airline it was, and so on. Altogether, this data is about 12 gigabytes. That's certainly not as large as the data set could be, but for our purposes, it's large enough to demonstrate working with big data. If you want access to the data yourself, you could click it from this link here. Keep in mind, this data is too big to fit in my laptop's memory or RAM, so we'll have to use our setup with big data. With this data, we'll do an example task. I'm going to collect a random sample of training data. I'm going to use that data to fit a model in R. And then once I have that model, I'm going to score it against test data that's still in the database. So that'd be data too big to bring into R. To do this, I'm using a very specific setup. For RStudio, I work for RStudio, but I'm going to use the RStudio IDE, well, the RStudio environment, to analyze this data. You're probably familiar that RStudio has a desktop IDE that you can download straight to your computer and use on your computer. I'm not going to use that. RStudio also has a server version. It has an open source server version, and it has a professional server version. And I'm going to use the RStudio Server Pro for today's demonstration. And this makes sense. If you are using massive big data sets, then RStudio Server Pro is the version of RStudio that you'll want to use. You will more than likely have multiple people on your team who need access to that data, so you want to use a server version. And then also more than likely you are a company that would care about the sort of things that RStudio Server Pro provides, like load balancing, security, administrative tools. And then we're also adding new features in the newest version of RStudio Server Pro, such that you can have multiple R sessions running, and your team members can collaborate together to edit the same documents. And it's easier to keep track of R versioning and to even audit the history of what's been done with the data. So that's what I'll use. I'm going to have a browser on my computer that's connected to an RStudio Server Pro set up in the cloud. The Server Pro is running R, and then I'm going to put my data in an Amazon Redshift database. To use the data, I'll have to talk to that database from R, and the way I'll talk to that database is with the dplyr package. There's a good chance you've heard of dplyr, and there's also a really good chance you've probably already used dplyr. dplyr provides a grammar of data manipulation that's very useful. It's a workhorse package for any data manipulation task. You want to calculate descriptive statistics, create new variables, subset your data. dplyr is the way to go about it. What you might not have known is that dplyr comes with a built-in backend to SQL. And you could use the dplyr backend to connect to a database management system, to transform your R code that you wrote with dplyr into SQL and pass it to your database management system. And you could also use this backend to collect results from the database back into R, where you could work with them locally. So these are the two steps that we mentioned in our general strategy. The other reason I'm using the dplyr package is the grammar that it provides that people use on a daily basis already makes a terrific front end for working with data no matter where that data is stored. You could learn this grammar. These are functions like subset, filter, select, and so on. We do have other webinars about data wrangling, and that's where you can learn the grammar yourself if you're interested. Here I won't spend time on that. But once you know that language, we're working in the background to make backends to SQL, Spark, other data stores, so that you could apply that grammar to data wherever it might live. So in other words, by learning dplyr, you're sort of investing in the future. It will be more and more useful to know dplyr because you'll be able to apply it to many different data stores. So how do you connect to a data store with dplyr? One set of functions that dplyr provides are these SRC functions, stands for source. And the way they work is you look at the language your database uses. So here Redshift uses PostgreSQL. dplyr has a function called source Postgres, which you can use to connect to a PostgreSQL database. The arguments for this function are just the things that you would need to connect to a database over a server. For example, the database name, the host, the port of the database, and then also your credentials for signing into the database. So I have some code here, but I'm going to jump over to RStudio Server Pro where I have the code as well, and we'll run that code. So here I have my web browser. This is just Google Chrome. I've connected to my instance of RStudio Server Pro at this web link. I've signed in already. I could sign back out if see how it works. I have credentials on the server, so I could sign in. And then all of the code in the slides today I've put here into an R script. The script is called webinar.r, and this is part of the material that we will make available. So in about 24 hours on our website, rstudio.com/resources/webinars, you'll find a recording of this webinar, the slides that I used, and this R script there. So you'll have access to all of these things. In this script, I'm going to use dplyr. I'm also going to use ggplot2 to make some graphs at the end. This is the code that I'm going to use to connect to the database. And the way it works is I use the code to create this object air, which will be a connection to this database. Now air exists. And then if I want to see what tables are in that database, I could use that air object to look. The dplyr function source tables tells me that this database has two tables. One's called flights, one's called carriers. Of course, your database can have many tables. And then the way dplyr works is if you want to work with one of the tables in the database, you create an object in R that can serve as a reference to that table, and use the TBL function to do that. So here I'm going to tell dplyr, create a reference to a table in the air database, or the database that air is connected to, using the flights table in that database, and save it as an R object, which I'm just going to call flights. Flights is now a connection to a table in that database. If I want to look at that table, I could call flights, and well, it's not called up there. And dplyr will fetch the first 10 rows of flights and show me those 10 rows. Now the table itself is, hit enter. The table itself is quite a large table. dplyr tells us it's 123 million rows. Those 123 million rows are not inside of R at this moment. dplyr just fetched 10 rows so I could look at the data and get a sense for what's in there. It tells me where the data came from, the sort of database at this address, how big the data is. It shows me some of the variables, and it shows me other variables that aren't shown because they run off the side of my screen here. Let me also go ahead and make a connection for the carriers table, and then return to the slides. So I use the source Postgres driver function, but dplyr already has driver functions for a variety of database languages, including MySQL and Google BigQuery, SQLite. And if you wanted to use dplyr and create a backend for a language that doesn't already exist, you could do that. There's a vignette in dplyr that tells you how to add your own SQL backend to it. And you could pull up that vignette very simply by just running this code here, the command line. And this is the vignette. It shows up in the viewer pane, and it's quite extensive. It tells you what you need to know to do this work. Once you've set up a table reference, recall that flights here was a table reference, you could use that reference as if it was the actual table. You could run your dplyr code here. This is all R code. You might not be familiar with this percentage greater than percentage sign, but this is code that works in R. It's called the pipe operator. And it's a great way to write concise code that does multiple things to the same data. So here, we're going to take that flights table, we're going to filter it, and then that pipe operator, just read it as and then we'll go filter it again on some more criteria, and then we'll go filter those results on a third set of criteria, and then we'll go select from all that these variables from the data set. Once we've done all that, we'll go store it up top into that object called clean. We come over here to our code. This code is in the script. I'm going to run it. Notice that this code runs really fast. In fact, dplyr is being lazy here. It's not actually doing this filtering back in the database. It's just saving everything into this variable called clean. And if I wanted to see what is in clean, you can see that it's an SQL query. So what dplyr has done is it's taken our R code, it's transformed it into SQL or SQL, and it saved it as a query. When I actually want to look at clean, or when it's time to actually use clean, then dplyr will run the code. And here dplyr runs the code over in the database, And then once again, it's only fetching back the first 10 rows of data to show me what the results look like. But the rest of the data is over in the database for me to use when I want it. And this is the results of cleaning up my data and just getting those few rows from the flights data set, which was much more extensive. And here we can see clean itself is only 6 million rows. This code here is really no different than code that you would use in R. And that's what we need to stress here. You just write your R code and dplyr converts it to SQL for you. If you know SQL or SQL, you can write your SQL yourself. And in some cases, you might want to do that. But in general, SQL and R are so similar, but still different enough that when you try to go back and forth between them, it's cognitively difficult. It's easy to make mistakes. It is very useful to just stick with one language the whole time. dplyr can transform its own functions into SQL, and it can also transform the basic operators in R, the basic math functions, comparisons, booleans, aggregations into SQL. Now, I myself could write an R package today and submit it to CRAN, and it can have its own set of functions. dplyr is not going to know about those, and it won't be able to translate those in SQL because it doesn't really know what they do. But the basic functions that you need to get work done, general purpose work, dplyr can transform into SQL for you. You could also pass into your R call functions that aren't in this list, and dplyr will just pass them as is to SQL. So you can write SQL functions there in your code. I mentioned that dplyr is doing some lazy execution features here that which really help if you're using big data. For example, you can imagine this sort of R code here. I'm not using the pipe operator, but if you're familiar with the pipe operator, I could simplify this into a single call should I want to. But here I'm filtering a data set, I'm saving as something, I'm filtering that, I'm saving, and so on. Each step here does something, but dplyr won't actually do any work until it has to show you the results of Q4 down here. This saves a lot of time. Nothing gets run unless it has to. But then when you need it, it will get run. And if you look at the query for Q4 down here, you see the query involves all the filtering commands down here where that were built up before we even got to saving something as Q4. The second thing that dplyr does is it only pulls back 10 rows to show you the data until you ask for the rest. If you want more than 10 rows, so you can work with all the data locally in R, you could do that by adding the dplyr command collect at the end of your call. Collect tells dplyr to just retrieve all the results and store it in R, so now we'll have a real data set in R to work with. There's another way to force execution. This time you force it on the database side, and that's collapse. If you put the dplyr command collapse into your pipe or into your code, then at the point you call collapse, dplyr will run all that code in the database that occurs before collapse, and then the code that occurs after collapse will be able to use the results that were collapsed with collapse. So for example, here we want to filter on a variable that's made in the mutate statement. The collapse command ensures that the database runs mutate to build the ADJ delay variable before you need to use that variable to filter. All right. So we know a little bit about dplyr now. Let's proceed with our task. I want to collect 1% of the data to use as training data to build a model on. And I want that to be a random subset. So this is how I'm going to do it. I've done this sort of thing a few times before, and I found that this code right here sort of ends up being a template, so it's pretty useful. I'm starting with that clean data I went with. I'm creating a new variable called x, and it's just using the random command from SQL to create a random number next to each row. Collapse the data so that random number appears in the table, and then I filter based on that random number to just 1% of the data here. And then I select everything but that extra column, which I don't really need, and I collect the results. So let's go over to RStudio and run this code. You'll notice since I'm actually collecting the results, it takes a little longer to run the code. The Redshift instance that we set up for today, and even the RStudio Pro instance, aren't provisioned with a lot of RAM. They're pretty small instances. If you attended New York Strata with Nathan and I, we did something similar there. We had much more suitable instances and things ran faster. So don't feel bad that it's taking a second or two today to run these commands. But now if I look at class, or if I look at random, I still only see the 10 rows. This is just dplyr's way of showing data. But in this case, it's a local data frame, and the remainder of the rows are there. 1% of this data is about 64,000 rows. If I wanted to look at the end of the data set, it's there. It's here in R. Tailed looks at the last 6 rows. And that's because I call collect at the end. Okay, so let's fit a model in R. The question I want to ask is, do some airlines make up lost time better than others? So it's not too uncommon that the flight leaves delayed, it departs delayed, as measured by the step delay variable. And then planes also arrive delayed. But it's possible to make up time between the two. And if the arrival delay is smaller than the departure delay, then that flight made up some time, it gained some time. And I want to see if some carriers are better at doing that than others. So I'm going to create this gain variable, which is just the difference in arrival delay and departure delay. And then I'm going to build a model using R's LM function. And I'm going to put the amount of initial delay and the distance of the flight in there as variables, along with unique carrier, the airline that used the data. The dataset I'm using is random. That's the dataset I just built. And then we can look at the coefficients over here. So here, I'm adding the gain variable to random, fitting my model. And then this code here, we don't really need to understand it. I'll just show you what it does. It takes the coefficients of the model, which we could extract in this format, and it turns them into a data frame. Let's do that. So what I've done is for each airline, each unique carrier, I've taken the slope of the carrier variable and added it here. I've also added the intercept, the distance slope, and the delay slope here to the model. You notice the intercept and the distance repeat for each one, but each carrier has its own unique score. Now this is useful because I'm going to use this as a lookup table to use with the data back inside the database to score each observation based on its unique carrier, its distance, its delay. Okay, so here's how I'm going to score the data. This is more dplyr code. Again, this is all R code. That pipe operator is an R thing. It is not a Redshift thing, it's R. dplyr takes this code, it turns it into PostgreSQL, sends it to Redshift, and Redshift applies the code there. Those of you not familiar with dplyr, I'm filtering out the data. That means I'm subsetting on rows. Then I'm selecting the data, which is subsetting on variables to a smaller, more targeted data set. I'm joining the coefs table, that's the lookup table I just made, to that data. I'm also joining a table called carriers. We haven't looked at that. It just replaces those codes with the actual names that we recognize, like JetBlue and Southwest. And then mutate is going to add a gain variable, and this go add a predicted score for each observation based on the model we came up with. And you'll notice that this predicted score is just a combination of the intercept from our model, the carrier score, and the distance score, all contained in the lookup table, multiplied by the actual distance delay and departure delay values for each row. I'm going to group that data by description. At this point in the process, that will be each unique airline gets put in its own group. And then I'm going to summarize the mean gain for each of those airlines. And I'm going to collect the results and save it as scores. So let's go ahead and do that. So here I am again working in R, sending the code over to Redshift to implement the code. It collects the results. Now I could look at scores. And I guess maybe it'll look a little better if I stretch this out. So unfortunately, US Airways has a really large name, which takes up a lot of space. All right, let's look up scores again now. Okay, so here's my data frame. It's just 3 columns, the names, the gain, the average gain for each of them, and the predicted average gain. So this is the real gain based on the data, and this is the gain based on our model. All this was computed in the database and brought back here into R. It used all 600 million rows, whatever we're looking at, subset to just the year 2008, and it did all that in the database. So you could use ggplot2 to visualize the results. The code on the previous slide makes this graph. What we see here is the actual gain experienced by each of these airlines in 2008, the predicted gain based on our model using just 1% of the data from before 2008, data only up to 2007. And if our model is exactly accurate, then each of the airlines would fall on this blue line, but you see they fall around the blue line. So now we could go and think about, well, why does our model fail for ExpressJet but work well for Southwest, and maybe improve our model. All right. If you wanted to take a table that you have made in R, like Query 5 or a lookup table, you could use the dplyr function copy to put it in your database, so it'll be there for everyone else who accesses your database. And then if you want to close the data frame connection after you're done using it, which is always a good policy to do, you just remove the object here. Instead of calling this DB, let's call this air. That would be your connection object. And then you run GC, which is the garbage collector. And that will close the connection, so no resources on the server side will be set for you to use. All right. So that's just an example of using dplyr, but like I said, there are many other packages that you can use. They use slightly different function names, as you can imagine, but this idea of communicating back and forth with your data store from inside of R will always be the same. And it lets you use your ability as an R expert to query data that might be humongous and might live in something like Hadoop or Spark. So the idea here, store your data outside memory in a data warehouse. Use an R package as an API to the data. For each of these, you normally create and work with the connection object, and then you close the connection when you're finished. So now that you can actually access data, and hopefully you have a feel for how this would look in real life, and that you could get results from big data, there's some other questions that come up about how you'd use big data. I'm not going to spend too much time on these things because in some ways they're a little bit like common sense, but because of that, that doesn't mean they're very useful to know, and it could save some time to think about. If you want to use big data with visualizations, only plot summaries of the data. There is no reason to plot raw data if you're working with big data, because visually the graphical bandwidth can't accommodate big data. If you have many, many values and you try to plot them on the same plot, they will obscure each other. So here's, we're looking at our gain variable based on the departure delays from our data set. This is only with the clean data set, which was smaller than the entire data set. And you can see for most of this graph, there's just a black blob. We can't really see where the weight of the points is because the points obscure each other. I can make the points a little smaller, a lot smaller, but if your data is large enough, you're going to have this problem no matter what because you're trying to look at the raw data. You could get the same information by just plotting a summary, such as a two-dimensional bin of that graph or a relationship line that shows the relationship of the points. So that's probably pretty obvious. The other thing that might not occur to you right away is that you can calculate those summaries, and you should calculate those summaries in the data store by calculating them manually. If you consider this bar graph over here, so this is just counting how many data observations occur for each carrier in our data set. So it's like the distribution across carriers of the data. If you're a ggplot2 person, you might recognize the code over here. This is how I made the graph. If you're not ggplot2 user, the same idea applies here. This is a bar graph. If you look at your actual data set, there's no count variable. That variable on the y-axis doesn't occur in the data. In this case, ggplot2 calculates that variable for you when you make the graph. Behind the scenes is actually creating a second data set that counts up the number of observations for each unique carrier, and then it's plotting that data set in the graph. You don't have to worry about it because ggplot2 is doing it. And if you just use bar plot or basic plotting in R, the same thing's going to happen. The graph is going to do calculations in the background to present the image to you. If your data is very large, that tool is not going to work very fast. ggplot2 wasn't set up to use big data. As far as I know, plot was not either. So to go from the first data set to the second step will be a time-consuming step. However, you could make the second data set yourself manually. Now, for those of you who use ggplot2, you might recognize that this step is the equivalent of using a stat. Stat's short for statistical transformation. It's in ggplot2 terminology. It refers to the way you transform your data before you visualize it. And you could actually decide in ggplot2 how you want to transform your data before you visualize it by setting the stat argument. Whenever your stat argument is something other than identity, that means ggplot2 is doing calculations in the background. And if you're using big data, I recommend that you avoid that. Only use stat identity with ggplot2. So by default, gmbar uses stat bin. That's not stat identity. But we could use dplyr to calculate the count for each of the carriers to make this data set. And we could collect this data set from our database management system. This is a superior way to do it because the database management system, which is designed to work with big data, will do the work for us, hypothetically, fast and quick. Then we could take this data, collect it into R, and make our plot straight from that data set. With ggplot2 here, you'd use almost the same code, but you'd specifically set stat equal to identity to tell ggplot2 you already have the count variables and they're stored in the y variable. And so here we can make the same plot a lot faster. Okay, I might have belabored the point. When it comes to publishing your results with R Markdown, specifically, and this also works in knitr because it's the same technology here, I recommend that you purposefully cache your code chunks that manipulate big data. If you're familiar with R Markdown or knitr, you can embed R code into your written reports. And you use this sort of code chunk syntax, and you can set options for each code chunk that you embed. One of the options is cache. By default, it's set to false, but if you set it equal to true, this behavior occurs. The first time you render that report, R Markdown will run the code in the cache chunk. It will save the results of that code in a subdirectory next to your report on your hard drive. It will also take a hash of that code chunk. The next time you run your code, R Markdown will consult the hash of the code chunk and the existing code chunk to decide if anything has changed. If nothing has changed, it's not going to run the code chunk. It's just go insert the results that it saved in your subdirectory. So here, this is very trivial code. It just makes your computer sleep for 5 seconds, and then it takes a random normal value. If you copied and pasted the text over here and put it into an R Markdown document on the left, you can recreate these chunks just by running the document. The first time we run it, we actually get a random normal value, 1.58. And the computer sleeps for 5 seconds before it does that. The second time, your computer is not going to sleep for 5 seconds, and the random normal value that the chunk delivers will be the same one from the first time, because it's not rerunning that code. It's just using the cached results. Okay? If it had run the code, almost certainly we'd have a different value there under rnorm. Well, if you're doing something that collects data from a database in your R Markdown report, which you should do, this is completely legitimate to do, you should also cache the code chunk that does that. That way, you only have to do the time-consuming step once, and every other time you run the report, you'll just use the results that have already been computed. If your code chunk ever changes, which would imply that the results change, well, then R Markdown will rerun it. R Markdown is smart enough to know when something changes, and it reruns, so you never have to worry about being out of sync. That's my first tip. The second tip is, if sensible, consider using a different language. You don't have to use R with R Markdown or knitr reports. You can actually set the engine language of the code chunk to a different language. Here I'm using Python, but you could use, C, Fortran, some varieties of SQL or Scala. And some of these things might actually let you do a big data task a little faster. But as we saw earlier, you can certainly use R to do big data tasks. And the last subject area that I want to cover with big data is using Shiny. So Shiny is a wonderful product for developing interactive web applications with R. But it's easy to write an inefficient Shiny app if you don't know what you're doing. And it's easy to learn what you should do. So let's just take a moment to learn that. When you create a Shiny app and you host it online, for example, with shinyapps.io or Shiny Server Pro, your application is hosted by a virtual server. And when someone comes along and visits your network address to use that application, the Shiny Server Pro sets up an instance of the server for them to use, and in that instance of the server, it opens an R session to maintain the app, and then your end user connects to that R session, and they use the app. If another end user shows up, then they could use the same R session, and perhaps several people will share the same R session. Well, R sessions are single-threaded, which means you get more users there. At some point, the server will set up a second R session to start handling new people so that no one's performance degrades or slows down. And at some point, the server might even set up a new virtual instance to handle more R sessions, and so on and so forth. So that's how Shiny is delivered through Shiny Server Pro and shinyapps.io. And this architecture is important. It matters because if you build a Shiny app, here's just a simple Shiny app on the right here, different parts of your code are going to be repeated a different amount of times based on what's happening over on the server side. So everything outside of that one little server function there will get run one time for each new R session that opens. For example, this is where you load libraries. That's something you do once per R session. It's where you define the UI for your app. You only need to do that once per R session. And it's also where you call shinyapps.io. If you put code out here, that code will be run the minimum amount of times possible. So this is where, if you can get away with it, you should put all your time-consuming connection establishing code for big data. Anything you put in the server function is going to be run more often. it's going to be run once for each new user that connects to your session, or each time a user connects back to your session. And you can see from my graphic, that's going to happen more often than our sessions will be set up. So this code will run more. If you unnecessarily put something here that could be outside a server, it's going to slow your app down. And then finally, anything you put inside a reactive function, like a render function, or event reactive or whatnot, the basic Shiny functions, will be rerun each time Shiny needs to re-render that plot or recreate that reactive expression and so on. Depending on what your users are doing, that could be quite a few times. This code will be repeated the most out of anything in your Shiny app, so you should only put things inside of a render function or reaction function if they need to be there. So by moving your code as far up to the top of this page as you can make your app work a lot faster. And if you're using big data, that's something that I think will improve your experience. The second two tips of advice for Shiny are the reactive expressions in Shiny cache their results, just like we were looking at with our Markdown. So they only rerun their results when something's changed. You could take advantage of that to save time. And then if you know you have an operation that's very expensive, put it behind a delay button or an action button. So Shiny doesn't automatically react and start that large operation until your user presses something that tells the app to go ahead and do it. Your users will find that more friendly. If you're familiar with the Shiny tutorial, it's at shiny.rcu.com, or this graphic from other places where I've taught it, these are these two parts of the reactive process in Shiny, using reactive expressions and using update buttons to delay reactions. So thank you very much for listening to all that. We have about 12 minutes left for questions.
So Garrett, shall we, let's see, we have some time left. Nathan, I see, and I think Tarif too have been answering questions along the way. You might just talk to that class 3 problem mentioned about, if I'm using a big data store that's ML. Let's see, we've got a few more coming in here. Any strategy there, to running it needs to run in the database, not so much in RAM. I think you mentioned it earlier, but you might just restate the class 3 solution there as we see it.
Sure. Why don't I give my thoughts on that, and then I'll ask Nathan for a second opinion. But if you have that class 3 problem where you need to analyze all the data at once as a whole, that is a non-trivial computer science problem if you're working with truly big data. That will be a feature of the software that you use to store the data with. I don't have any recommendations about which software you should use. All R can do is encapsulate the algorithm that you want to apply to the big data, and then the actual reality of breaking it down and applying it to all the data at once. It's something that the software you pair with R is going to have to contribute to the process. So that's not much of an insight. But Nathan, what would you add to that?
There's a lot of big data technologies for parallelized algorithms in the database. Some of those depend on R, and many of those do not depend on R. So, it depends on what data store you're talking about and what tools are at hand and how you would really like to do this. The one that's most common is SQL, and SQL will actually get you a long ways. Obviously, you're probably going to have a hard time building, linear models in like a MPP or SQL compliant database, and that's why a lot of vendors like Oracle and I think what Vertica was mentioned, Teradata, they have their own methods for doing some of these things in the database. So we can't give you a definitive answer. A lot of it depends on what you have and what you're trying to scale out to.
There's some other questions that are popping in here that might be interesting to the wider audience. In particular, I'm seeing a number of things about dplyr and what it might support. You want to comment on the different databases that and big data sources that dplyr has connections to?
Certainly. So I did put a slide in there that lists the supported backends for dplyr at this moment. We as a company plan to invest more to expand that list, to add more backends. And then also we are looking for people to contribute backends, and especially companies that have a database like Oracle or whatnot to contribute. So I guess most of the questions are specific. Does it work with this or that? I see one for Oracle. Oracle does have its own R-based package. I don't know if dplyr works with Oracle yet, but you could use the package that Oracle disseminates. I think it's R Oracle.
Yeah, it actually does. There's a dplyr backend for Oracle.
Excellent.
Great. There are a number of questions on, is this functionality available with the open source products as well as the professional products from RStudio? And the answer is yes, just generally to those kinds of questions. There are some additional capabilities in RStudio Server Pro that are particularly good for teams of data scientists, but you can do what Garrett showed with the desktop product, the open source desktop product, or the open source server product, and dplyr certainly works with those products as well.
Yeah, everything we did at the command line today, you could do on all three of the RStudio IDE products. The additional features of Pro are embedded into the GUI, outside of the command line, I'd say.
Yeah, and there are some other questions about recommendations on big data sources, or which or the last one about AWS. We don't particularly recommend things to because they're so specific to your needs. But we have a lot of materials on our website. If you just Google, they'll often come up about working with things like Amazon or working with various backends. So hopefully those doing a little bit of research will help you find a few articles from us on our website or out there in the wild.
Roger,
all right.
there was a question that has since disappeared, but I wanted to address it because I think maybe I explained something incompletely. The question was, for our Markdown documents, when you're caching it, how does it know when the data's changed? And I just want to make clear that our Markdown doesn't actually know if the data changed. If it changed on your server side, or like in your SQL database, our Markdown can't tell that. Our Markdown knows if your code chunk changed. So if you add an additional filtering criteria or different select criteria, that's what our Markdown can see. So if your data is changing on the database side, you might not want to cache that chunk. That would be a limitation of caching. That's all.
Okay, thanks. I saw that too. That's a good catch. We're still getting a few more, but I think we're going to call it a day here and just wrap up. Thank you so much, Garrett, and everyone, Nathan and Tarif and Bill, for answering questions along the way. We tried to keep up, and I think we mostly did. I'll just end here with, if you are interested in our commercial products, and we certainly hope you are, there are some significant capabilities in RStudio Server Pro, particularly if you're a team of data scientists. So if you're working for an organization and you're looking to collaborate with others, you might be using multiple versions of R. You might have the need to run a big data query, and you want to kick off a session and still be able to keep working. These are some of the features that are in the preview product of RStudio IDE Server Pro that we'd love for you to take a look at. And then on the Shiny Server Pro side, if you're deploying Shiny applications, of course, security, management, scalability are all advantages of our professional product there. You can certainly take a look at our website and see the comparisons between our open source products. The open source products have tremendous value, and we have millions of users actually at this point, but we certainly appreciate those who look at our commercial products and find them useful and help support our business in that way. So thank you very much for coming today, and we hope to see you again. Don't forget the sessions coming up on RStudio Essentials for the IDE. We're very excited about that. It's going to take a couple months, but please, if you can't attend live, take a look at those as they come out. If you're wanting to learn all the essentials for working with the RStudio IDE, you're going to find a lot of great information in the next six webinars. So with that, you know how to reach us. These are many of the places that you can stay in touch with us and keep informed. Please subscribe to our blog in particular. That's the best place to learn about our product info. We keep it pretty much down to the essentials of essential news and product. So please go there. And otherwise, have a great day. Thanks for attending today.